So a couple things left out of my video would be recursive sequences and partial sums. Not so sure that I left out the other one or not, but let's take care of a couple of things now. Recursive sequences are kind of neat, and they're defined in a different way. Now, keep in mind that typically speaking, when we're working with sequences, we'll name them, the elements like a sub 1, a sub 2, a sub 3, come on, a sub 3, etc. And we have a pattern that we recognize or a formula that we use, and that tells us what anyone is. They'll tell us what a sub n is. A sub n is maybe n squared plus 1 or something like that. You get a nice formula that you can directly plug into. Recursive sequences are different. To get any term in a recursive sequence, I have to know the previous term. So let's take a look at problem number 16 here. This is my general form of the terms in this sequence. It's going to start out with a sub n equals a sub n minus 1 divided by 6. And then it also tells us what a sub 1 is. So that's all you need to get started with a recursive sequence. Typically speaking, once you're given the first term, you can find the next term. So a sub 2, well, a sub 2, if I put in a 2 here for the n, then a sub 2 is going to be a sub 2 minus 1 over 6. Now, 2 minus 1, I don't think you need to bust out your calculator for that. That's a sub 1 over 6. So basically, to get the second term in the sequence, I got to take the first term in the sequence and divide it by 6. So what's the first term in the sequence? Well, that's right here. So it's negative 24 divided by 6, or negative 4. So that's a sub 2. Now that I have a sub 2, I can find a sub 3. A sub 3, well, a sub 3 is just going to be a sub 2 divided by 6. So it's going to be negative 4 divided by 6, which is negative 2/3, and so on. You can keep going as high as you want. To get any term, you got to take the previous term and divide by 6, and that's what this is saying. So a sub 3 divided by 6 would be negative 2/3 divided by 6, and let's see, what's that going to be? Negative 1/9. Let me just do it out. Negative 2/3 times 1 over 6. As you divide by a fraction, you multiply by the reciprocal. The 2 and the 6 will cancel, leaves me with negative 1/9, and so on. So the object here is not necessarily to give you an exercise in arithmetic, but to help you understand what these things are. So let's try another one just like this. Let me pause for a second. Does this first example look okay? You kind of understanding where that's coming from? Cam?
Oh yeah, I understand. Yep, I understand this one.
Okay, good. So let's take a look at problem number 17 then. So maybe I can just move this down a little bit. So problem 17, we've got a new formula right here. And it says, if I want to know any term in the sequence, I got to take the previous term and double it, and then add 1. So let me give myself kind of a new palette here. And we'll look at this problem. So a sub 1 is 1. So if I want a sub 2, then I got to take 2 times a sub 1 plus 1. 2 times a sub 1 plus 1. Well, a sub 1 was 1. So for a sub 2, I get 3. And then we can keep going. If I want a sub 3, I need to take 2 times a sub 2, the previous term, and add 1. So maybe you can race ahead here. What do you think a sub 3 is going to be?
Won't it be 7?
Yep, 7. And so on. A sub 4 would be 2 times a sub 3 plus 1, 2 times 7 plus 1 is 15, and so on. And so that's your recursive sequence. And they're pretty cool. They're very powerful. A lot of programming, computer programming, is done with recursive sequences and recursive calls. So it's a really handy kind of idea, definitely. So good on that one? Good on recursive sequences?
Yeah, that's pretty straightforward.
It's not too bad once you see it, I hope. So,
it's not, no.
Now, the next one that you might see I haven't quite discussed is partial sums. And partial sums really is just adding up the first so many terms of a sequence. So, for instance, with S3 is going to be the sum of the first 3 terms in this sequence. So let's take a look at that. S sub 3 is going to be 2 plus 4 plus 6. So that's going to be 12. S sub 4 is going to be 2 plus 4 plus 6 plus 8. So the first 4 terms in the sequence, and that's going to be 20. And so on. S sub 5, 2 plus 4 plus 6 plus 8 plus 10 is 30. So nice. Pretty straightforward. Pretty straightforward. I hope that completes any little missing holes that I have in the video that I put online. Looking okay there with that S sub n kind of notation? S sub n is the sum of the first n terms. This is what I don't like about this thing, is that it just doesn't write very well sometimes. S sub n, whatever. The sum of the first n terms of a sequence. Nice, nice. So how are we looking with partial sums? Pretty good on that one, Cam?
This is this is very easy too.
Cool.
That was easy.
Yes, I hope you heard that, and I hope it came through.
Yeah, I heard that.
Yeah, you've been missing that, I'm sure, because it's been a while. It's been a while since we've been face to face. Let me give you, we were talking about history. Let me give you like one little historical thing. There's a guy by the name of Fibonacci, and he was a very influential early mathematician around 11th century, 12th century, I think, maybe. And he looked at a problem of breeding rabbits. And I'm not going to try and pull it up here, but essentially he started looking at, how many pairs of rabbits you would have after successive generations. So you start with 1, then they have offsprings, and eventually their offsprings can, multiply, and then eventually have 2 breeding pair, the original, and then after 1 month, another pair. And the way you start getting the terms in the sequence is by adding up the previous 2 terms. So the sum of these terms gives us the next one. The sum of these 2 gives us the next one. The sum of these two gives us the next one, and so on. So what do you think the sixth term in this sequence would be, Cam?
1 + 1 + 2, 4, 8.
You're just looking at the last two terms. So
oh, it would be 8.
2 yeah, so the next one would be 8, and so on. And so these numbers are really very famous. They're called the Fibonacci numbers. They come up everywhere. You'll see them in the number of seeds in a sunflower. You'll see them in investing. They're just all over the place. They have so many amazing properties. It's really cool. I mean, one of the things that we didn't get to do is, well, yeah, actually, it will still be part of this course, is Pascal's triangle. So you see the Fibonacci numbers in Pascal's triangle. So they're just all over the place. And there's a little bonus material here for you there. Fibonacci. Maybe we'll use that as an extra credit kind of thing at some point. So yeah, hey, thanks for letting me share that with you. So we're good on those?
Yep.
All right. Well, something else you haven't heard in a while. See ya. So if you want to do some of this stuff on your calculator, you can. The first thing you want to do is you want to go to mode and then slide down to Linus's function. Oops. And then all the way over to this last option here, which is sequence. So that's going to turn your calculator into something that works with sequences. And if you exit out of here, and I think I can just do that with the clear button, then let's take a look at our y equals key. Our y equals key looks much different, doesn't it? So
yeah, it does.
Yeah, it really does. Now, if I had a sequence that was, say, I don't know, -1 to the nth power, and you look at your calculator and you start searching for n, but guess what? N is right here where your x was. If you notice, that button that we push for x has a lot of different letters on it. It's x, it's t, it's theta, and it's n. And it depends on what mode as to what you're going to get here. When I press n, bam. Or when I press that key, I get an n. And we're going to multiply that by, let's just do something simple, n squared. So every time I press that, I'm getting n squared now. So, okay, that's kind of cool. And let's see, what else do I want to do? Let's graph some of this stuff. Hi, Aspen. Now, again, when you go to the window, you're going to see some different stuff. You've got n min and max. That should be pretty good. It has a min and a max for x, a min and a max for y. So, hi, this is going to be great on my YouTube video, Aspen. So I threw the bone out the door, and he's looking at it, he's like, I know you're going to shut that door behind me. I know. Sorry. All right. Well, let's just hit plot and see what happens, because we're going to get a few of these things to graph, but I don't think it's going to be wide enough to get all of them. So let me hit the graph key, and yeah, we got a couple of them. I didn't get all of them. So let's try this. Let's try zoom and then 0. Zoom 0 gives you zoom fit, and maybe that'll do things for us. And there you go. There's the graph of our sequence. So keep in mind, it's going to start with -1, and then 2 squared is 4. -1 to the second power is going to keep that positive, and then -9, then +16, then -25, +36, -49, 64, etc. So you're getting this zigzag pattern here to your numbers. In fact, let me make that a little bit easier to kind of follow along. Instead of working with the square of numbers, let's just work with a constant number. What's your favorite number, say 50 to 100?
We'll go with 13.
All right, I was hoping for something between 50 and 100.
50 and 100. Oh, that's right.
50
Okay, so let's try 75.
75. All right, so let me delete this one. Delete. One more time. Delete. All right, and let's put in 75. So what's this sequence going to do? Well, depending on if you have an even exponent or an odd exponent, it's going to plot 75, right? So let's take a look there. And there you go. So with an odd exponent, you're at negative 75. With an even exponent, you're at positive 75. So bam, bam, bam. So it's kind of nice. You can actually plot these things with or plot your sequences. There's a lot of other tricks and commands you can do here. Let's take a look at our list menu real quick. Second list, operations, sequence. Let me remind myself how to do sequence. So let me go down here. And I don't think I've set this up. If you hit plus, you might have your catalog help set up, and it'll tell you how to, use this command. So the way to use this command is to type in the expression, then your variable, and then where it begins and where it ends. And there's an optional thing at the end here for your increment. So if I press enter, that should plug things in here for me. Maybe not. Escape. All right. Now let's press enter. There we go. So I'll type in the expression. The expression, let's do it simple. Let's do 2n plus 1. There's my expression, comma, n. That's my variable. Comma, where do I want this to begin? Well, instead of just, mundane 1, how about if we begin it at 2? And I want it to go up to 5. And bam, there you go. It lists out the terms in the sequences. Now suppose, let's do that again. So if I hit the second key and then the enter key, and I'm going to change it up a little bit. I'm going to go between 1 and 7, but this time I want it to skip around. I want it to increment by 2. So I'll do a comma 2 here. And there you go. So it's plugging in first n equals 1, then n equals 3, then equals 5, and finally n equals 7. So it's skipping your even numbered terms. What else can we do with this? Well, you can do the list, and then operations would be math. Let's do the sum of this sequence. So, now, can I do this? Can I go back up here? Yeah, I can do the sum. No, it won't. Didn't let me do that. No, it's not letting me do it. So let me do 2 operations in a row. Let's do the sum of a sequence. So I'll go back to list. And then option number 5. Oh, wow. It's giving it to me in a nice form here. That's kind of nice. So my expression was 2n plus 1. Variable was n. Starts at 1. Ends at 7. And the step is by 2. And go down here one more. I'm going to paste it in. So it's just giving me the same command or same thing that I just had in a menu form. I'll put a right parenthesis out of habit, so I keep my parentheses balanced. But the nice thing now is that when I press the enter key, oh, bam, it adds all those up. 3 and 7 is 10, plus 11 is 21, plus 15 is 36. So your calculator can do all kinds of cool things with related to series and sequences. And those are just a couple of them. So how do those look?
Nice.
Nice.
Good. That's awesome. It makes life a lot easier. I was doing everything manually, so that works.
Yeah. Yeah, it does make life easier. Oh. All right. You know, it keeps on telling me that I can pause the recording by hitting Alt and then P, but it never does. It never works. So I'm curious to see at the end of this meeting if I'm going to have like 4 different files or just one. We'll find out. So find the indicated terms of arithmetic sequence with a given description. So a sub 50, let's start with that. A sub 50 is 1,050.
Yep.
And the common difference is 7, so D equals 7. Boy, this is just really annoying that this isn't writing better. 7, no, that's not helping. All right, so let's keep in mind the general term for an arithmetic sequence is a sub n equals a sub 1 plus n minus 1 times d. And well, we know what d is, right? So it's really a sub 1 plus n minus 1 times 7. That's our a sub n. But in order to be able to find the first and second terms, we're going to need to know what a sub 1 is, right?
Mm-hmm.
A sub 1. A sub n. This is just killing me. A sub n. Well, we know what the 50th term is. So I know a sub 50 is 1,050. And that's going to equal a sub 1 plus 50 minus 1 times 7. You agree there?
Yep.
All right. This is just not working. Well, the only unknown here is a sub 1. So let's solve for that. We get 1,050 is a sub 1. This is really driving me crazy. A sub 1 plus, that'd be 49 times 7, I think it's 343. You can check me on the calculator.
Yep. 343.
343. And when I subtract that, I get 707 for a sub 1.
Okay, that makes sense. I know what I think I got tripped up on, cause I tried to do the elimination method and I was sort of similar, but I didn't do something, it was something I was missing. I think I was trying to do, I don't remember, but it was almost close, but not like this.
Sure. Well, what would a sub 2 be if a sub 1 is 701?
A sub 2 would be, let's see, 707 plus 2 minus 1 times 7. So basically 714?
Yeah, 714. Yeah, all you have to do is take a sub 1 and add 7, right? Because
Yeah.
7 was our common difference right there. I mean, once we have a sub 1, we know what the formula is altogether. So altogether, it's a sub n equals a sub 1. Actually, I shouldn't put a sub 1. I should just put 707 plus n minus 1 times 7. Now, you can, I mean, some people do distribute this, and, if they distribute it, then you get 7n minus 7, and then the 701, or excuse me, the 707 minus 7 just becomes 700. So you could write it as 700 plus 7n, and that's equivalent. I just don't like it as much because with this other method, with the other way of writing it, I can just look at my sequence and know what's what. I can look at it and I can know what the first term is, and I know what the common difference is. And it stands out to me as an arithmetic sequence, whereas if I write it like this, well, then I got to think, I mean, not much, but I got to think briefly about what a sub n is. So, yeah, I'm just not as big of a fan of that. But, I mean, it is equivalent, and it is an arithmetic sequence just like the other one. So, cool. Hey, Kim.
Thank you.
How you doing today? Got any questions for the group? And Brian, welcome. Same thing.
No, I just came to tune in. I'm going through some things, so I'm just tuning in.
Okay, that's good. I'll post a Zoom. There's a lot of good things in this meeting. I talked about recursive sequences. I talked about partial sums, showed some calculator tricks. So yeah, definitely a good thing to review. Brian, how about you? Shout out to you. Any questions there? No audio from Brian. That's okay. Let me pause things here.